Welcome to Math TV with Professor V. In this video, we're going to look at 4 examples of evaluating integrals using partial fraction decomposition. Now, if you haven't already watched the introductory video lecture on partial fraction decomposition, I will link it right here. It shows you how to do some more basic integrals that involve partial fractions. Also, if you forgot how to do partial fraction decomposition completely, or perhaps never even learned it in pre-calc, I'll link that video right here. There's 4 cases that you need to recognize and be able to work with. So the purpose of this video is just to work through some more examples and work through some more spicy integrals, as I like to call them, the fun ones. So let's get started. First example here, we have indefinite integral 3x squared minus 11x plus 4 over x cubed minus 3x squared plus 2x dx. All right, so first things first, I notice I have a rational function. Degree of the denominator is higher than the degree of the numerator, so I can proceed with the partial fraction decomposition. In order to do so, we have to factor the denominator first completely. So notice I can take an x out from all the terms, and we'd have x squared minus 3x plus 2 left over, and that factors further. So now I'm going to write everything out. We have 3x squared minus 11x plus 4 over x times, and then I need to factor this trinomial here, which is going to factor into x minus 2 times x minus 1. All right, now looking at each of the factors in the denominator, they're all linear, meaning x is raised to the first power, and none of them are repeated. So this is one of the most straightforward cases. I'm just going to have constants in each of the numerators here for my decomposition. So a over x plus b over x minus 2 plus c over x minus 1. Nice. Now in the next step, you want to clear out all your denominators. So we're going to multiply by LCD. In this case, that's x times x minus 2 times x minus 1. And everything in this equation gets multiplied by that. So on the left-hand side now, we're just going to be left with 3x squared minus 11x plus 4. And then on the right-hand side, we'll have a times x minus 2 times x minus 1 plus b times x. Notice the x minus 2 will cancel, so I just have x minus 1 left, plus c times x minus 2. All right, this is a good place to pause. You have the option of multiplying everything out, but I think it's easier if we use a different method to try to solve for a, b, and c by substituting in different values of x that would make each of the factors 0. So first one we can try is letting x equal 0. Why did I pick that? Well, if I let x equal 0, notice here, this entire term and this entire term will go to 0. So you're going to substitute in values for x that would make each of these factors of the original denominators 0. All right, so if x is 0, on the left-hand side, we're just going to be left with a 4. And this is going to equal a times 0 minus 2, that's negative 2. 0 minus 1, that's negative 1. Plus this whole term's just going to be 0, plus this is 0. All right, so then if I simplify further, we have 4 is equal to 2a. So a is going to be equal to 2. Save that, and then we're going to repeat the process. So now we let x equal 0, then we can let x equal 2. So let's go ahead and substitute in 2 for x. Where do you substitute that in? After you've cleared out the denominators from the equation right here. Okay, so I'm going to plug in 2 for x now. So we have 3 times 2 squared, that's 3 times 4, so 12, minus 11 times 2, that's 22, plus 4. What's that going to equal? Well, notice if I plug in 2 for x, this factor here is going to be 0. So this whole term is gone. Bye-bye. So we've got a 0 plus b times 2, right? We're plugging in 2 for x. And then 2 minus 1, that's 2. Oop, that's 1. Plus, and this last whole term is going to go to 0 because we're plugging in 2 for x again, remember? 0. All right, love it. On the left-hand side, we've got 12 minus 22, that's negative 10, plus 4, that's negative 6, equals 2b. So b is equal to negative 3. Okay, almost there. Last one, what do we need to let x equal? Can you see? Why, yes, we need to let x equal 1. Bravo. So we're going to let x equal 1. And then now substitute that back into the blue equation that I boxed after we cleared the denominators. So if x is 1, we'll have 3 times 1 squared, so that's 3, minus 11 times 1, that's 11, plus 4, equals, now remember x is 1, so this factor is going to be 0, wiping out this whole term. Bye-bye. Plus, again, x is 1, so this second term is also going to be gone. Plus, we have c times 1 times 1 minus 2, that's negative 1. All right. Now let's see, 3 minus 11, that's negative 8, plus 4, that's negative 4, equals 0 plus 0, that's going to be negative c left over on the right-hand side, which tells us c is equal to positive 4. Okay, great. That one wasn't too bad. So now we're going to go back to the original integral, and what I'm going to do is replace the constants, a, b, and c, with the values that we found. Remember, a we found was 2, b we found was negative 3, and c was 4. So I'm going to rewrite the original indefinite integral using my partial fraction decomposition. So we have now the integral of 2 over x, since a was 2, b was negative 3, so that's minus 3 over x minus 2, plus 4 over x minus 1 dx. All right, now can we anti-differentiate each of the terms that we see here? For sure. I mean, they're all just basically going to be ln absolute value of whatever's in the denominator, and then just throw these constants out front, right? No u sub or fancy maneuvers necessary. So we can just jump straight to the final answer, okay? So antiderivative of 2 over x would be 2 natural log absolute value of x. And then minus 3 natural log absolute value of x minus 2 plus 4 natural log absolute value x minus 1, and don't forget to put plus c. All right, how was that one? Did you love it? It was pretty straightforward. It's a basic example. I just wanted to get us all warmed up. The next 3, the spice level will increase, okay? So this was just like a crunchy pepper. I've got a jalapeno coming up, and then we're gonna bust into a serrano at the end, okay? Yes. All right, so next one I wanna look at here. Example 2. These are all gonna be indefinite integrals, just so we can focus on the technique. But you can also do definite integrals with these. We've got 3x to the 4th plus 15x squared plus 5 over x cubed plus 5x dx. All right, I have a rational function, but do you see how the degree of the numerator is degree 4, whereas the degree of the denominator is only degree 3? That means it is not time to do partial fraction decomposition yet. Oh, no, no, no. The degree of the denominator needs to be higher than the degree of the numerator when you apply partial fraction decomposition. So if it's not, you must long divide first. Did you forget how to long divide polynomials? Have no fear. I'll link a little video here that'll get you through a little refresher. Okay, it's not too long. I'm just going to assume you remember. Okay, so here we've got x cubed. I need a 0x squared as a placeholder. And then we have 5x. And then we have no constant. And this is going to get divided into 3x to the 4th plus, I need a placeholder for that x cubed, plus 15x squared plus 0x plus 5. All right, remember when you're doing polynomial long division, you only look at the leading terms. So just think to yourself, what do I have to multiply x cubed by to make it 3x to the 4th? That's right, just a 3x. And then that 3x gets multiplied by everybody in the divisor, everyone sitting outside. So we have 3x to the 4th plus, this would be 0x cubed, plus 5x times 3x, that's 15x squared, plus 0x. Nice. Then we subtract the bottom row from the top row. The furthest left terms should cancel out. And then the second term's also canceled. This cancels. This cancels. So we're pretty much done. Bring down the 5. And this is our remainder. How do I know it's a remainder and I can't keep dividing? Well, 5, that's just a constant. It's degree 0, right? There's no variables attached to it. And our divisor sitting out here is degree 3. If the divisor is a higher degree than whatever you're left with, you are done. That's your remainder. Okay? So how would you write out the result? It's 3x plus 5 over, what were we dividing by? X cubed plus 5x. You don't have to put all the placeholders in for your final answer. Okay? So this is your little remainder. It looks so harmless. Okay, now, if we're going to integrate what we found here as the result of doing the long division, we still need to apply partial fraction decomposition to the remainder portion, right? You know how to integrate 3x. That's no problem. We got that. Should I put a little happy face? Yay. But 5 over x cubed plus 5x, ooh, yeah, we need to do partial fractions because can't u sub, sadly, right? If I let that be u, I would need, too bad there's no 5x squared in the numerator, right? Oh man, it's fine. That's why we got partial fraction decomp to save the day. So here we go, it's partial fraction time. And remember, you need to factor that denominator completely. So 5 over x cubed plus 5x. How would you factor that? Yep, just take an x out. So you've got x times x squared plus 5. And so our setup for this case would be a over x plus, notice x squared plus 5, that's an irreducible quadratic. So the numerator needs to be a linear expression of the form bx plus c. Again, if you forgot about this, that's in that video that I linked earlier, just explaining how to do partial fraction decomposition. Okay, from here, the next step is the same as in the first example. You're going to multiply everything by the LCD, which is x times x squared plus 5. You want to be fraction free. So on the left-hand side, we're going to have just 5 left over equals a times x squared plus 5 plus bx plus c times x. Good, good. Now, if you'll notice here, since we have an irreducible quadratic, there's nothing that we could plug in for x that would make that first factor equal 0, right? We'd have to use imaginary numbers, and we're not working with those right now. So another technique to try to solve for the constants is to multiply everything out. Okay. So let's do it. So we've got 5 equals ax squared plus 5a plus bx squared plus cx. And what you do to proceed from here is you collect the coefficients for like terms on both sides of the equation and set them equal to each other so you can solve. What am I talking about? I'll show you, don't worry. So find all the terms on the left-hand side that are coefficients of x squared. So you might be thinking, I don't know what you're talking about. There's no x squareds on the left-hand side. You're correct. There's a 0x squared on the left-hand side. So 0 must equal, where are the x squareds on the right-hand side? Well, I have an ax squared and a bx squared. So 0 must equal a plus b, right? The coefficients of the like terms must be equal on both sides of the equations. What about x? Do you see any x's on the left-hand side? Nope, me neither. So you've basically got a 0x hiding there. What terms involve x to the first on the right-hand side? Only this last one, cx. So that means c must be 0. And then last case would be your constants. So on the left-hand side, I do have a constant this time, 5. And what's my constant term on the right-hand side? 5a. That's the term that doesn't have any x's attached to it, right? So it's a constant. Ooh, well that tells me a is equal to 1. And remember, I already know c is 0. And if a is 1, since a plus b is 0, then b must be -1. And now basically we're done with the partial fraction decomposition. So that's an alternate approach that you could use, okay? So now let's put everything together. What do we have now? Do you remember from the long division we had that 3x hanging out first? Don't forget about him. 3x. So we've got 3x plus a was 1. So this is going to give us 1 over x. And then b is -1, so I'm going to put minus x over x squared plus 5 dx. All right, now let's see how we would anti-differentiate each of these. 3x, no problem. 1 over x, no problem. X over x squared plus 5, that's no problem, but we're going to have to use u substitution. So let's do a little aside. If you have integral of x over x squared plus 5 dx, I know to use u substitution because the denominator is degree 2, and you see how the numerator is 1 degree lower? That's the most perfect time to use u substitution, because if I let u equal x squared plus 5, then what's du going to be? It's 2x dx, which is fabulous because we've got that x dx right there. So 1/2 du is x dx, which means this is going to give us integral. I usually like putting the constants outside, so let's put that 1/2 out there. Du over u. And then what would this be? This would be 1/2 ln absolute value of u plus, I'll call it C1, which is 1/2 ln absolute value x squared plus 5 plus C1. Okay, why am I calling it C1? Because this is not my final answer. I want to save just writing plain old C for my last answer that I'm going to report, which means now we have antiderivative of 3x, 3/2 x squared, plus What's the antiderivative of 1 over x? ln, absolute value of x. Then we have minus, okay, all of this stuff that we had here. Minus 1/2 ln. You know, I don't need absolute value around x squared plus 5 because there's no way that's going to be negative, right? If you square something, it's not negative, and if you add 5, then we're good to go. So I can switch those to parentheses. If you don't, it's not wrong. It's just not as clean as can be. And then I'm going to put plus c. Okay, how was that? Now, when you get more practice with integrating, you might be able to identify that, oh, this is going to involve a u sub. I'm just going to have a 1/2. I'm going to have ln, absolute value of the denominator, and maybe you won't even need to write all this out aside. You can just do it in your head. I'm not even joking. Once you've done enough integrals, that's going to start happening to you. So if you're in my class, I have no problem if you're going to skip those steps, but just check with your professor before you take such liberties, okay? All right, nice. This was just, you know, moderately spicy, jalapeno. I've got a serrano for you. Oh yes, example number 3. Integral 3e to the 4t plus 12e to the 2t plus 4 over e to the 2t plus 4 dt. Okay, this one's going to take some manipulation. The numerator, I'm staring at it, and I notice these two terms, I can factor out a 3 and an e to the 2t from, but this poor little 4 I can't do that with. So what I'm inclined to do now is split this integral into 2. So I'm going to split it into 3e to the 4t plus 12e to the 2t over e to the 2t plus 4 dt. That's going to be integral 1. Plus integral 2 will be 4 over e to the 2t plus 4 dt. Okay, and we're going to tackle each of them separately. I know integral 1 looks more frightening, but it's actually way easier than the second one. So check this out. For integral 1, I mentioned initially we can factor out a 3 from both those terms and an e to the 2t. So if I do that, if I take out 3e to the 2t, then what am I going to be left with in the numerator? If you take out e to the 2t from e to the 4t, you're just going to have e to the 2t left plus, yes, just a 4. And then in the denominator, we still have that e to the 2t plus 4 dt. Oh my goodness, do you notice something? I'm excited. Look at this. E to the 2t plus 4 gone. Bam, bam. And then now we're just left with integral 3e to the 2t dt. Okay, and then I hope at this point, I mean, you're in advanced calculus, guys, you shouldn't need to u sub just because of this silly little 2 in front of the t, right? I mean, if you waste your time, u equals 2t, du is 2 dt, and then all that's going to happen is you get a 1/2, okay? By now you should have noticed that that's what happens. So please just jump straight to the fact this is going to be 3/2 e to the 2t, and I'm going to say plus c1, right? I like to save that final plain old c for the final answer. Okay. Yay, integral 1 is done. That looked so painless. Integral 2. What to do? So we've got 4 over e to the 2t plus 4 dt. It's not looking so cute, right? You can't just ln stuff because you see terms in the denominator, okay? Don't go down that path. That's an illegal move a lot of calc students make, and the math police will be hot on your tail. What we're going to do is make a change of variables, use some substitution, and then we're going to end up busting out some partial fractions. Oh, yeah. here's the idea, okay? I'm going to let u equal e to the t. Then du would be what? Yeah, it would be e to the t dt. And you might say, I don't think that's going to help. Well, check this out. So we've got 4 over e to the 2t is the same as e to the t squared, right? Plus 4 dt. Okay, so that means we have integral 4 over, if u is e to the t, this is going to be u squared plus 4. And then what about this dt, remember? So dt here is equal to du over e to the t. And remember, e to the t is equal to what? It's equal to u, yes. So that means dt is equal to du over u. So now I have du over u down here. Ooh, kind of weird, but I like it. Now we have integral 4 over u times u squared plus 4 du. And now we're set up where we can apply some partial fraction decomposition, okay? So here we go, partial fraction time. Why don't you guys pause the video and see if you can figure out the decomposition, okay? And then check back in. All right, good. Did you pause it? I hope you tried it yourself. It's one thing just to sit there and watch me solve them all. It's another when you got to do it on your own, right? So we've got 4 over u times u squared plus 4. That's going to equal a over u plus, you need bu plus c over u squared plus 4, right? Good. I'm going to go through this quickly because I'm assuming you already worked through this and you're just checking your work. So we're going to multiply by u and u squared plus 4. And then on the left-hand side, we'll just have 4 equals, so the u's will cancel. I'm going to distribute right now. au squared plus 4a plus, and then here this u squared plus 4 will cancel. So I'm just going to distribute the u. And we'll have bu squared plus cu. Okay. Again, since one of the factors was an irreducible quadratic, I'm going to solve for a, b, and c like I did in the previous example, the second one. So for the squared terms, there aren't any on the left. So 0 must equal a plus b, right? Good. And then the linear terms, there aren't any on the left. So that must equal c. And then constants, let's see, 4 has to equal 4a. Oh my goodness, we're getting the same values as last time. How strange. Or maybe not strange, huh? So a is 1, c is 0, and b is -1. Did you get the same thing? I hope so. And that means now we're left with integral 1 over u minus u over u squared plus 4 du. Okay, I'm not going to hold your hand so much. It's time to become an independent advanced calculus student. Antiderivative of 1 over u. Yes, ln, absolute value of u. Minus, you guys, this should be super familiar. We literally just did almost the same exact antiderivative in the last example. It's just this 4 was a 5. I don't want to do a u substitution. Well, first of all, I can't because I already used up the variable u. So you're going to have to pick another letter, okay? And t is used up from the get-go. And honestly, at this point, you should be able to recognize the pattern and not even need to do it. You're going to have a 1/2 ln of the denominator, and I don't need absolute value because I know this isn't going to be negative, plus c2, all right? If that just was whoosh, way over your head, go back to the last example where I did break down the substitution so you can follow along where that 1/2 came from. But you should start recognizing these patterns now. because as the integrals get more complicated, you don't want to have to keep doing a u sub over every little baby thing. And then remember from the very beginning, u was equal to e to the t. So let's go back and replace that here. So ln absolute value e to the t minus 1/2 ln of u squared is going to be e to the 2t plus 4 plus c2. And then ln of absolute value of e to the t, I mean, e to the t is not negative, so we didn't need absolute value there. This is just the same as ln of e to the t, which will just be t, minus 1/2 ln e to the 2t plus 4 plus c2. So now, final answer, because this was just the result from the second integral, is as follows. We had 3/2 e to the 2t, right, from the first integral, plus t minus 1/2 ln of e to the 2t plus 4 plus c, where c is equal to c1 plus c2. Voila. Did you like this one? It's not that bad. It's just, it looks so scary in the beginning. You might think, I forget it. But the plan of attack of dividing it up was really essential. Okay, so on that note, I've got another spicy one for you, and then we'll be done. And it is kind of similar to the last one that we just did in the initial approach, okay? This is like, yeah, it's Serrano level, maybe habanero. I don't know. We'll have to find an appropriate pepper to classify it. You can let me know in the comments your rankings of them, okay? And the appropriate chilies. Example 4. It's going to look frightening. Please don't be scared. We've got integral. I love these. Okay, x plus 5 squared, tan inverse of 2x plus 4x cubed plus x over 4x squared plus 1 times x plus 5 squared dx. Holy moly. Okay. I already give you a hint that you're going to break it up. You know, how do you want to group things this time? You see how this has an x plus 5 squared in it, as does this denominator? Let's split it right here. You see what I'm saying? I hope so. Here we go. 2 integrals. We've got first one, x plus 5 squared, tan inverse of 2x over 4x squared plus 1, x plus 5 squared dx, plus, that's the first integral. Second integral is going to have 4x cubed plus x in the numerator over 4x squared plus 1 times x plus 5 squared dx. Okay, let's tackle them one at a time. Are you ready? All right, first one. Anything you notice with integral 1? Remember we split it up a certain way because we wanted to cancel some stuff out, right? Yeah, so the x plus 5 squared will cancel out. So let's go ahead and do that. Bam, bam, gone. And then things should start looking kind of interesting, somewhat familiar. I mean, we've got a tan inverse of 2x. All right. And then this 4x squared plus 1 in the denominator. And I'm feeling a u sub. Why am I feeling that? Because I know I learned my derivatives a long time ago, and I made sure I memorized them. The derivative with respect to x of tan inverse of x is 1 over 1 plus x squared. And so since I have a 2x here, that would mean this would end up being a 4x squared, which is exactly what I see in the denominator. So I feel like u sub will work out beautifully with this problem. In that case, we're going to just let u be the the numerator, excuse me. So let u equal tan inverse of 2x. And then just be careful when you find du because we have to use the chain rule, right? So you're going to have 1 over 2x squared plus 1 times, what's the derivative of 2x? It's 2, so don't forget that, dx. That's not exactly what we have. I'm going to have to move this 2 over to the other side. So 1/2 du is equal to dx over 4x squared plus 1. Ooh. Do you see it now? Ooh, okay. So here we go. We've got that 1/2. Let's put it outside. Integral. In the numerator, instead of tan inverse of 2x, just sweet little u, minding its own business. You know what? I don't even need a fraction bar, huh? And then that kidney bean that I drew right here, that was my 1/2 du. I already got the 1/2 outside, du. Bam. Wow, wow, wow. This is such a nice little integral. Antiderivative of u, 1/2 u squared. We already have a 1/2 sitting outside, so this is 1/4 u squared plus, that's right, c1. And then just go back, we're going to replace u with what it originally was. What was it? Tan inverse of 2x squared plus c1. Okay, integral 1 is done. Nice. Now let's move our attention to integral 2. You see it? 4x cubed plus x over 4x squared plus 1 times x plus 5 squared. I want you to notice you could take an x out here. Did you see that initially? Maybe not. Maybe you were so traumatized, huh? Okay, so let me rewrite it now with the numerator factored so you can see. So we've got integral x times 4x squared plus 1 over 4x squared plus 1 times x plus 5 squared dx. Yay! Look what we can do, you guys. Cancel out this 4x squared plus 1. Fabulous. Okay. Then we have integral x over x plus 5 squared dx. Okay. Now from here, you've got some options. Yeah, you can do partial fraction decomposition for x over x plus 5 squared. Okay. If you did, notice in the denominator we have a repeated linear factor. So the setup would be as follows. X over x plus 5 squared equals a over x plus 5 plus b over x plus 5 squared. Okay, so that's one way you could do it. Then you would multiply everything by x plus 5 squared and be done. I'm going to show you something else just so you have more tricks up your sleeve, okay? Or you could do this. We have x over x plus 5 squared. And what I'm going to do is add 5 and subtract 5 to the numerator. And then watch how I'm going to regroup the terms. So I'm going to put this x plus 5 over the denominator, x plus 5 squared. And then I have minus that other 5 over x plus 5 squared. And the whole point of doing that is now the x plus 5 in the numerator will cancel with one of the ones in the denominator. So we have 1 over x plus 5, just to the first now, minus 5 over x plus 5 squared. And that's what you would get if you sat there and did the partial fraction decomposition. A would be 1 and B would be negative 5. Okay? Sometimes doing this plus or minus 5 business, though, makes students nervous. So you don't have to do it. I just want to show you some options. It's pretty slick, though, right? I always feel a little fancy when I bust out that maneuver. Okay, so from here, If you hated that, then just do the partial fractions. Make sure you can get the right constants. And we're going to be integrating 1 over x plus 5 minus, you know how I'm going to write the next term for you? I'm going to write it as 5 times x plus 5 to the negative second dx. Okay. Antiderivative of 1 over x plus 5. ln, absolute value, x plus 5. And you guys, please do not use sub for this next one. You should be able to anti-differentiate this in your head. X plus 5. If you were just integrating x to the negative second dx, you would add 1 to the exponent, divide by the new exponent, which is the same as just multiplying by negative 1, right? And you'd have plus c. Well, does it make a difference that now we have x plus 5 instead of plain old x? If you sat there and did a sad little u sub, I say sad because, I mean, it's really just a waste of time. If u is x plus 5, du is dx, all that you're accounting for is this plus 5. I mean, who cares? Can't we just account for that as is? So now we're going to have plus 5 times x plus 5 to the negative first. Yeah? Do you see it? I hope so. Plus c2. And of course, I'm not going to leave it like that. It looks so gross. So ln, absolute value, x plus 5 over x plus 5 like that, plus c2. Yes, yes, yes. Here we go. Okay. So now let's put it all together. I feel like we forgot what the original integral was. Did you forget? Let's rewrite it just to be such thorough little mathematicians. Integral. What was it? It was scary. X plus 5 squared tan inverse of 2x plus 4x cubed plus x over 4x squared plus 1 times x plus 5 squared dx equals, you're going to have to go back through your notes, find that first integral. I have it here written down. I don't want to keep scrolling, make you nauseated. 1/4 tan inverse of 2x squared plus ln, absolute value, x plus 5 plus 5 over x plus 5 plus c, where c equals c1 plus c2. Okay. I know I really pushed you in this video. Like, I didn't break down every little detail. This is an advanced video. If you need more breakdown, that's cool. I have plenty of videos for you there. But once you're in Calc 2, you're an advanced calculus student, I want you to start generalizing, seeing more patterns, being more elegant in your solutions, and not using really basic tools when it's really unnecessary. You should start recognizing patterns more. Okay? So hope you enjoyed it. Hope you had fun. I like to have a good time when I'm doing math. It's one of my favorite things to do. And I'll do some improper integrals soon. I know those are tricky for everybody. We'll get through it in a good way. If you have other integrals you want me to evaluate or solve for you, we can do them together. I'm thinking we should start like a problem of the week or something like that. Give me your ideas. You can always email me mathtv at mathtvwithprofessorv@gmail.com. I'll put it in the description, and then you can follow me on Instagram, same handle. Okay? Take care, everyone. Don't forget to give a thumbs up and subscribe if you haven't already.